Buckle up. Let's run through 10 levels of insane paradoxes. Level 10, the Raven Paradox. All right, let's dive into one of the most perplexing paradoxes in science and logic, the Raven's Paradox. It challenges the very way we think about evidence and how we confirm scientific theories. It's deceptively simple, but when you look deeper, it can really bend your mind. Here's the basic setup. Imagine a statement like, all ravens are black. Now, this is a simple universal claim that we can test by observing ravens. Every time we see a black raven, it seems like we're confirming the truth of the statement, right? Well, that's what Hempel thought too. Now here's where it gets weird. According to logic and confirmation theory, the statement, all ravens are black, is logically equivalent to saying all non-black things are not ravens. That's the key idea. So, what happens when you see something that isn't a raven, but is non-black? For example, let's say you see a red apple. This apple, being non-black, technically supports the idea that all ravens are black. Sounds absurd, right? But according to the logic of confirmation theory, seeing that apple is actually confirming the truth of the statement, all ravens are black. Here's why. When you see a red apple, you're observing something that's not black and not a raven. So it confirms, by the rules of logic, that this object fits the condition that all non-black things are not ravens. In simple terms, every time you see a red apple, you've confirmed all ravens are black by fulfilling the logical equivalence of the statement. Level 9, the omnipotence paradox. Let's shift gears to something a bit more divine. Imagine an all-powerful being, a being that can do absolutely anything. This being can create worlds, move mountains, control the universe. And here's the kicker. This being is challenged with a simple task. Can it create a rock so heavy that even it can't lift it? Pause for a second and think about that. If this being can create a rock it can't lift, then, well, that means there's something it can't do. Lift the rock. But if it can't create the rock in the first place, then there's something it can't do. Create the rock. You see the issue here. No matter how you twist it, the concept of true omniscience and omnipotence doesn't hold up. The omnipotence paradox makes you ask, is there a limit to power? Or is logic the true master? Level 8. The Sorites paradox, also known as the paradox of the heap. Next up is a paradox that really messes with your perception of the world around you. Ready? Imagine a giant heap of sand. You can picture it, right? A big mound of sand just sitting there. Now, start removing one grain at a time. After you remove one grain, is it still a heap? Of course it is. Now, remove another grain. Still a heap? Yep. But wait. Keep removing grains, and soon you'll be left with just one grain of sand. So, at what point does it stop being a heap? Where's the line between a heap and just a pile of sand? This is the Sorites paradox, also known as the paradox of the heap. It forces us to rethink how we define things. What counts as a heap, or a pile, or tall, or bald? You see, some concepts don't have clear boundaries, and that's where the paradox begins. It's like trying to define the exact moment someone becomes bald. Where's the line? You can't draw one. Level 7. Zeno's Achilles and the tortoise paradox. Now, let's talk about something that confuses even the brightest minds. This one's from ancient Greece. It's called Zeno's paradox, and it's about motion, time, and, well, how the heck we even move through space. Picture this. Achilles, the famous Greek warrior, is racing a tortoise. To make things fair, the tortoise gets a head start, say 10 meters. Achilles is way faster, so you'd think he would easily overtake the tortoise, right? But here's the problem. Zeno argues that Achilles will never catch up to the tortoise. Why? Well, by the time Achilles reaches the point where the tortoise started, the tortoise has moved a little bit forward. When Achilles reaches that point, the tortoise has moved even further ahead. And this keeps happening, step by step, endlessly. Every time Achilles gets to where the tortoise was, the tortoise moves forward a little more. According to Zeno's logic, Achilles will never catch up. But, of course, we know that's not true. So what's going on? The issue lies in dividing distance into infinite steps, leading us to think that time must also be infinite. But infinite things can have a finite total. This paradox laid the groundwork for calculus, yes, the very thing that helps us solve this paradox today. But in the process, Zeno's paradox asks us, what does it really mean for motion to be continuous? Level 6, the unexpected hanging paradox. Here's one that plays with your mind, especially when it comes to predictions and expectations. Imagine you're in a courtroom and a judge tells a condemned prisoner that they will be hanged at noon on a weekday next week, but the execution will be a surprise. The key is that the prisoner won't know the exact day of the execution until the morning it happens, and the judge also says that the execution will be a surprise to the prisoner, meaning the prisoner should not be able to predict the day. At first glance, you might think, okay, that's odd, but possible. But the prisoner begins to think about it, and here's where the paradox begins. The prisoner's reasoning goes like this. If the hanging were to happen on Friday, I would know by Thursday night, because Friday would be the only day left. But then it wouldn't be a surprise, right? So it can't be on Friday. The prisoner now eliminates Friday. Then they think, well, if it can't be on Friday, then it must happen before Friday. So if the hanging were to happen on Thursday, I'd know by Wednesday night, because Thursday would be the last day left. But then it also wouldn't be a surprise, so it can't be on Thursday either. The prisoner continues this reasoning for each day of the week, ruling out Thursday, Wednesday, Tuesday, and Monday. By the time the prisoner is done, they have logically concluded that the hanging cannot happen at all. But we're not done yet. On Wednesday, the executioner shows up and the prisoner is completely shocked. The hanging does in fact happen, and it's a surprise. So what went wrong? The prisoner, in trying to predict the hanging, used a perfectly logical chain of reasoning to eliminate every possible day for the execution. And yet, the execution happened exactly as planned, completely defying the prisoner's expectations. Level 5. The crocodile paradox. Picture this, a crocodile lurking by a river, and one day it grabs a child. The child's parent begs the crocodile to release their child. The crocodile, being unusually logical and clever, strikes a deal with the parent. I will return your child if and only if you correctly predict what I will do next. Now, the parent, in a desperate attempt to get their child back, thinks carefully and makes a prediction. The parent says, "You will not return my child." At first, it seems like a reasonable prediction, right? The parent is trying to outsmart the crocodile. But now, here comes the paradox. Let's break it down. The crocodile has agreed to return the child only if the parent's prediction is correct. But here's the catch. The parent predicted that the crocodile will not return the child. Now, let's follow the consequences of this prediction. If the prediction is correct and the crocodile does not return the child, then according to their deal, the crocodile must return the child. But if the crocodile returns the child, the prediction would be incorrect because the parent said the crocodile would not return the child. But what if the prediction is incorrect? If the prediction is wrong, the crocodile doesn't have to return the child. But if the crocodile doesn't return the child, that would make the prediction correct, which means the crocodile must return the child in order to fulfill the deal. Do you see the issue now? It creates an endless loop of contradiction. It's self-referential reasoning at its finest, and it raises some serious questions about how we make predictions and deal with contradictory conditions. If a contract or a system sets up impossible terms, how does it work in practice? This paradox is used to explore ethics, language, decision-making, and even artificial intelligence. Something to think about, right? Level 4. The Ship of Theseus Paradox. Here's one that's going to make you think about identity. Picture this: the Ship of Theseus, an ancient Greek ship. Over time, every single piece of wood on the ship gets replaced with new planks, one by one. Eventually, every part of the ship is new. So the question is, after all the replacements, is it still the same ship? Well, let's take it further. Imagine someone gathers up all the old discarded planks from the original ship and rebuilds it exactly as it was. Now there are two ships. One is the new ship with all its new planks, and the other is the one rebuilt from the original aged wood. Which one is the real Ship of Theseus? You see, this paradox isn't just about ships, it's about identity itself. When something changes over time, like your body or your memories, at what point does it stop being you? It gets even more fascinating if you consider the idea of mind uploading. If we could transfer someone's consciousness into a new body, would they still be the same person? The Ship of Theseus forces us to confront deep questions about what it means to remain the same over time. So, is it the parts that define the ship, or is it the continuous existence of the ship itself? Level 3. The Grandfather Paradox. Time travel. One of the most mind-bending topics out there. But time travel doesn't always come with the happy endings we see in movies. The Grandfather Paradox asks a simple but very disturbing question. What happens if you go back in time and stop your grandfather from ever meeting your grandmother? Seems harmless enough, right? But here's the catch. If your grandfather never meets your grandmother, then your parent is never born. If your parent is never born, then you're never born. And if you're never born, then how the heck did you go back in time in the first place? See the problem? This paradox is a nightmare for time travel theory because it creates a logical contradiction. If you alter the past, you erase your own existence. But if you erased your existence, then how could you have altered the past, could you? It's like a time loop that eats itself. Philosophers and scientists have come up with some theories to deal with this paradox. Maybe time fixes itself when you try to change it. Or perhaps every change you make just creates a new timeline, one where you never existed. But no matter how you slice it, the Grandfather Paradox challenges everything we think we know about time and causality. Level 2. The Lottery Paradox. Let's talk about a probability paradox that really makes you question logic. Imagine you're in a lottery. There are 100,000 tickets, but only one will win. The odds for winning for any given ticket are really low, 0.01% to be exact. Now, here's the paradox. The odds of any single ticket winning are tiny, so it feels rational to believe that all of the tickets will lose. But wait, if you believe that all the tickets will lose, then you're essentially predicting that none of the 100,000 tickets will win, even though one has to win. So how can you believe every single ticket will lose and still know that one must win? The lottery paradox shows how our logic can be inconsistent when we try to apply it to large systems. The more likely we think something is to happen, the more we tend to predict that it won't happen. But probability doesn't work in the way we think it does when applied to systems with large numbers of outcomes. It's a reminder that our minds aren't built for handling large numbers, and sometimes probability isn't as intuitive as we think it is. Level 1. The Twin Paradox. And now the grand finale, the ultimate paradox from Einstein's theory of relativity. This is the twin paradox. Imagine you have two identical twins. Let's call them Alice and Bob. Alice stays on Earth, and Bob hops into a spaceship that zooms off at near the speed of light. Bob travels for a while, then turns around and comes back to Earth. Now here's the crazy part. When Bob returns to Earth, he should be younger than Alice. Why? Because time moves slower for objects traveling close to the speed of light. So from Alice's perspective, Bob should have aged less than she did. But hold up. Here's where it gets even wilder. From Bob's perspective, he's the one at rest and it's Alice and the Earth that are moving fast. So shouldn't that mean Alice is the one who's aged more? So when they reunite, which twin is actually younger? Well, the paradox is resolved when you realize that Bob's journey involved acceleration and deceleration, things that Alice didn't experience. Bob's time was affected by this, while Alice's wasn't. So when they finally meet, Bob is indeed younger than Alice. This is a real phenomenon, proven by experiments with high-speed particles. Time dilation is no joke, and it's one of the weirdest, most mind-bending consequences of Einstein's theory. And that's it for 10 truly insane paradoxes that will break your brain. But wait, we've barely scratched the surface. These paradoxes show us that reality is much stranger than we ever thought. Time, space, identity, none of these concepts are as simple as we once believed. So, what do you think? Which paradox did you find the most mind-boggling? Let me know in the comments below, and if you enjoyed this brain-melding adventure, don't forget to like, share, and subscribe for more videos like this.